My name's Guy. I'm from VectorBlox, and we build FPGA-optimized processors and accelerators. And so we've started building a RISC-V processor, and it's completely open source. We call this ORCA. This is named after a statue in the Vancouver Convention Center, and you can see the view behind it in the Convention Center is really nice. If you ever have a chance to go to a conference there, I highly recommend it. One of the reasons I like this statue as representative of our processor is it's built in a pixelated way, implying it's got a lot of building blocks that put it together. And so that sort of implies something like Lego, which could be highly configurable, which is what our processor is all about. Also, we've dreamed a bunch of different backronyms for ORCA, and we'd be happy to take suggestions on additional backronyms. We want to make it a recursive backronym that unfolds to lots of different possible explanations. What we're going to do is going to put this on a very small FPGA. This is an ICE40 Ultra FPGA with just 3,500 lookup tables and 4 hardware multipliers. The chip itself, I checked on DigiKey, is less than $5 in unit prices. If you want to buy 1 million of them, you can get them much cheaper because these are actually embedded into Samsung smartphones, Google Glass, and MacBooks, and other high-volume devices. So these can get very, very cheap. So you could put a RISC-V, and get a RISC-V at ASIC level prices by putting it in a very small, cheap FPGA. So we have an RISC-V 32 with IM extensions, hardware multiply, software divider in about 2,000 lookup tables, which is just over half of the device. And this is a low-performance device. It runs at about 20 megahertz, which is a typical circuit speed for this particular FPGA. So that's one instance of what we have. That's the FPGA, by the way. It's really tiny. It's just a couple millimeters on the side. It's got to fit in cell phones, remember. So what we've done is a highly parameterized implementation that is ideally suited for FPGAs, and we're making it portable across different FPGA vendors and families of devices. And it is fully open source under a BSD license, so feel free to take it and use it however you wish, and please contribute back upstream so that we can make this ever better. Here's a comparison on different FPGAs for our implementation. On the ICE40, it's about 2,000 4-input LUTs. On a Cyclone 4, it's about 1,600. And on a Stratix 5, it's about 540 ALMs. The clock speed goes up to 240 megahertz on the Stratix 5, and it gives you about 200 MIPS of performance with a MIPS per megahertz of about 0.87. This is still under development. We are using instruction RAMs and block RAMs, not caches. And we don't have our branch prediction set up yet, so we're expecting further improvements in performance as we go forward. If you want to compare it to other RISC-V implementations, they're not really as FPGA optimized as they could be, whereas ours is. So on 4-input LUT architectures, we're the smallest between Zscale, Pico, RISC-V, and ORCA. We run at the fastest clock speed, or close to matching the Pico RISC-V at 125 megahertz. And we get the fastest dry stone MIPS out of all of these. Compared to FPGA-based soft processors, we looked at against the Altera Neos 2. We are slightly smaller in a similar configuration. We're slightly slower in the clock speed, and we're not quite as efficient in terms of MIPS per megahertz, but as I said, we have to enable our branch prediction and stuff like that. So it will get better. The important thing is here, we're in the same class as Neos in terms of size and speed, and that's where we want to be. If you look at the RISC-V architecture space, there's tons of options. There's 32, 64, 128 bits. Minimum, you have the I instruction set, but you can add M, A, F, or D in a binary fashion, and then Q, L, B, T, and P. They're giving you 2 to the 9 possible choices there, or options. And then you can add the compact instruction set encoding C. For RISC-V alone, there's 3,072 possible chips you can build, or architecture instances you can build. That's a lot of possibilities. But then when you go to implementation choices, like in the FPGA, you have a hardware-software multiplier, hardware-software divider, a shifter, which is 1 bit per cycle, or a single cycle, or maybe somewhere in between. The performance counters are spec'd at 64 bits, but you can implement them in 32. Maybe leave them out at 0. 4 or 5 stages of pipelining, forwarding from the ALU or from ALU and other functional units. So just this list here is 144 more possibilities times the original 3,000, removing the redundancy for the I instruction set. We have 221,000 possible processors you can generate here. It's a massive design space. Okay, if you're going to build an ASIC, the problem is you got to pick one of those and put it in your ASIC. So you got to find the best one that's the best trade-off for everything. The user doesn't have any choice, and that leads to compromises for certain applications. The beauty about FPGAs is we can leave the parameterization fully in there, and the user can choose the best one for their application. So you get the best performance and best area out of it. But yeah, that design space is a little overwhelming with 200,000 options. Here's an idea of what the design space looks on a Stratix 5 chip. We have 64-bit performance counters, 32-bit performance counters, or the performance counters left off. The vertical axis is execution time. Why does this change execution time? Well, it changes the clock speed you can run this at. It impacts the Fmax. On the x-axis, we have the area, and you can see the smallest is 550 ALMs, and the largest is 700 ALMs. Those 64-bit counters add a lot of area. It adds almost 40% to the area. So for an FPGA implementation, this is something you really want to have optional, or you want to put 32-bit counters in there instead of 64-bit, and then trap on overflow and handle overflow in software. Similarly, if you want to do 4 pipeline stages or 5, you get different performance. The 4 pipeline stages runs at a slower clock speed, so you get a slower execution time on your Drystone benchmark. You do it in 5 stages, and it goes faster, which is lower in the graph, but it also uses more area. So you have to have a trade-off there of area for performance. And ideally, you want to be on the bottom of that curve as close to the origin as possible. And the point of all of this is really that when you're designing a processor, if you're designing for an FPGA, that will migrate very nicely to an ASIC. But if you design a processor for an ASIC, it doesn't necessarily migrate nicely to an FPGA. You have to be aware what the costs are in the FPGA space to be able to make good trade-off decisions. And so what we like to do is optimize everything for the FPGA first, and if you want to go and move that to an ASIC, it'll be a pretty good result, and that's the order that we like to do things. Just as an example, let's suppose we're building a register file out of discrete flip-flops. You have to have 32 bits times 32 registers. There's 1,024 flip-flops. And then you have to have 32 32-to-1 muxes, which is another 352 4-input lookup tables. That 352 4-input lookup tables is 15% of our area for our processor. That's a lot, or 20%. So muxes are very costly. You want to avoid these at all possibilities. So for the register file, instead, we build it out of the block RAMs on the FPGA. We'll use one read and one write port. The block RAMs tend to have registers on the output of the block RAM, which is great. That gives you the ability to use that for a pipeline flip-flop for free. The problem is the write port cannot forward data to that read port in the same clock cycle. And so you have to do that forwarding externally in additional logic. Here's an example of our overall pipeline for a 5 or 4 stage. To create the 4 stage, we just delete the pipeline latches in the middle there for creating the separate forwarding stage. Our instruction fetch and our data load store goes over a Wishbone or an Avalon interface. So what I'd like to do is suggest that maybe there's some changes or thinking we can do around RISC-V to make it a little bit better for FPGAs. The embedded spec is great if you want to build an ASIC, but it saves nothing for the FPGAs because we're using block RAMs for our register file. The area is there already. Also, the divide is very expensive in FPGAs. In all of the trade-off graphs, the points all out to the largest area, those are the ones with a hardware divider. And so you see that's 2,500 LUTs versus the smallest one, which is 1,600 LUTs. The divider itself is about 600 LUTs, which was very big. If you're writing software for an FPGA-based RISC-V, be aware that your shifter might be really slow and only 1 bit per cycle. In fact, the software multiply routine was written with a 31-bit shift in there. And that made Drystone run really slow. So we contributed a change to the software multiply routine to use an AND instruction instead. And this greatly sped up the software multiply on FPGAs. For the privilege arc spec, we've been looking at this for a long time. And we find that there's a lot of these CSRs that take up a lot of state. And they all have to be built with those discrete flip-flops and big muxes. So they take a lot of area. And those 64-bit counters are really big as well. This places a lot of pressure on area. I think what we should do for FPGAs is try and define a small set of the spec that we want to rely on, and then a full spec and maybe a medium as an intermediate point. We're not likely to run hypervisors or something like that on an FPGA-based RISC-V, so maybe we can consider that in the medium spec, for example. So finally, we've developed a RISC-V family called ORCA. It's a free BSD license. It's portable across FPGA vendors, and it's FPGA optimized. Keep in mind when you're doing RISC-V things that FPGA and ASIC optimizations are different, and the FPGA architecture space dictates certain design choices. I know RISC-V tries to be independently designed of the target technology, but a lot of the decisions guiding RISC-V are unconsciously being driven by the known impact on an ASIC implementation, not on the known impact on an FPGA implementation. And that's the end of things. Well, I'd like to add that Lattice has generously donated a number of their ICE40 breakout boards. So if you would like one of these, and especially if you want to contribute to our open source CPU, please ask us. We'll give you one of these guys. Joel is from VectorBlox, if you want to stand up, and Tom is from Lattice over here. You could also go to them in order to get one of these devices. Our processor is currently on GitHub. And thank you. Any questions?
Do you have an idea why Jan Gray's designs are fewer LUTs and higher clock rate?
His is even smaller than what we have. He's not taken into account making it portable for different FPGA families. He's hard-coded it. He hasn't made it portable for different FPGA families. He's hard-coded it specifically for that architecture. And he goes in at the LUT level and programs the lookup table contents at the bit stream level, which is very, very detail-oriented and not really portable. So he's also an incredible hacker and has done a much better job than we have in general. So I bow to his excellence in all regards in this matter.
You might want to revisit your comments about whether RISC-V fits FPGAs well, though. There's evidence that it can, right? So,
in the demonstration system that you've got here, are you using Lattice peripheral IP?
We're using some Wishbone IP, I believe, from Lattice in that, yeah, for an LED controller and for a UART. So I think I removed a slide. It is a drop-in replacement for Neos. It has an Avalon interface. It's also usable in Lattice, except we've upgraded the Wishbone to Wishbone 4, so we can't quite backport it to the Wishbone 3 stuff that's in the Lattice design environment. But we do operate with their IPs. We'll have a Xilinx and a micro-semi version, hopefully, in the future as well.